We are now on the third page of the review packet. And these are concepts that we will see in the future. If you can't forget that we have a final coming. The final is going to be comprehensive, at least for the second quarter, although it certainly can't hurt for the first quarter. We can't be forgetting the stuff that we've been learning. That's very important to remember what we've covered over the year, especially those who are going on to AP or who are taking a Chemistry 2 SAT or SAT 2 Chemistry. That's extremely important. So, but anyway, we still have a final coming. Everyone has to take it. I don't buy into the idea that those who get A's for every quarter don't need to take the final. I think we're all in this together. We should all take the final. If you got an A every quarter, you should have no problem with the final either. You're not supposed to just be remembering this or learn this stuff and forget it and not remember it for the rest of the year. That's not how learning goes in my opinion. All right, now that I've given my speech, benzene reacts with oxygen to form CO2 and H2O. This is a nice combustion reaction. How much oxygen is required for the complete combustion of 1 mole of benzene? So first I would write my unbalanced combustion equation. Now, if I, just looking at this now, if I put 6 here and 6 here, that would mean 6 hydrogens would be 3 H2Os, but I see that I have now an uneven number of oxygens. So if I wanted to actually truly balance this, I'm probably going to need 2 of these and 6 waters. That would give me 12 carbon dioxides. So that's 12 carbons, 12 carbons, 12 hydrogens, 12 hydrogens. Now I have 6 oxygens plus 12 oxygens. I'm sorry, no, 24 oxygens. That's 30 overall oxygens, which would mean that I would have 15 O2s. And that can't be reduced any further. Now, if I were really savvy, if I remember my thermochemistry equations, where it would be the heat of combustion of 1 mole of benzene, I'm allowed to actually do something like this. Which is also allowed. So if I'm talking about the complete combustion of 1 mole of benzene, I have to keep it as 1 mole of benzene. I can't have 2 moles of benzene. 15 halves is now 7.5 moles. So there's my answer. That's how much oxygen is required to balance, to ensure that benzene combusts completely. Benzene is a fairly carcinogenic compound, so if you are burning it, you want to make sure you eliminate all of the benzene. Carbon dioxide and water are not nearly as dangerous as benzene to human health. All right, now, a 25 milliliter sample of 0.15 molar silver nitrate, this is this is molarity, moles per liter, is reacted with a 3.58 sample of calcium chloride. Which of the following statements is true? So if I'm aware here, 0.15 moles of silver nitrate would be in 1 liter of silver nitrate. I'm going to have a much smaller number in this particular situation. So what is my strategy here? I would suggest turning grams of calcium chloride into moles. This is a good old stoichiometry problem. So 3.58 grams times 1 mole over calcium is 40, chloride is, 1 chloride is 35.5, so that's 72. 40 plus 72 is 111 grams. So now my 3.58 times, did I move it out of the way? No, not too badly. I'll actually, while I'm here, I'll slide this up a bit. Slide it up a bit more. All right, so 3.58 3.58 divided by 111 is 0.0322 moles of calcium chloride. Does all of that fit on my screen? Yes, it does, just barely. Now, how many moles of silver nitrate do I have? Again, 0.15 equals X over 0.025. Where did my 0.025 come from? Molarity is moles over liter. That's how many liters I have. So now, (0.025) times 0.15. So X in this case is 0.00375 moles. Now the question is, which one of these is the limiting reactant? In order for that to happen, I have to actually find my mole ratio. What is my mole ratio? What is my reaction? AgNO3, that's silver nitrate, plus CaCl2. These are both aqueous. This is a double replacement reaction. If I looked at my solubility tables, I'd see that silver chloride is an insoluble compound. And all nitrates are soluble, so calcium nitrate remains aqueous. So looking at this now, I can tell it's not balanced. I have 2 chlorines, 1 chlorine. I'm going to need 2 silvers in order to balance this. Remember, silver's +1, chloride is -1. That's calcium chloride. If I do this, I have two chlorides, 2 chlorides, 2 silvers, 2 silvers, 2 nitrates, 2 nitrates, 1 calcium, and 1 calcium. I'm balanced. So that means for every mole of calcium chloride, I need 2 moles of silver nitrate. So if I have 0.03 moles of calcium chloride, I need 0.06 moles of silver nitrate. I can already tell right now I don't have that much silver nitrate. For all of my silver nitrate to react, I need half of that amount. I can tell that I have that half. So silver nitrate is the limiting reactant. I know that. Calcium chloride is definitely not the limiting reactant. Silver chloride is an insoluble compound. So the only possible answer here is B, that silver nitrate is the limiting reactant and silver chloride precipitates. Okay. Next one we should remember is specific heat. 37.5 gram piece of gold at 83 degrees Celsius is added to 100 grams of water at 22 degrees Celsius in a well-insulated cup. What is the temperature after the system comes to equilibrium? The specific heat capacity of gold is 0.129 joules per gram per degree Kelvin. So again, we have our Q equals M cat or MC delta T. I want to find out the energy. Okay, let me just adjust this for a moment. Now, good old specific heat problem. However, a couple other things are going on here. So I have heat coming out of the gold and going into the water. So whatever heat comes out of the gold is heat that goes into the water, which means heat equals heat. MCAT equals MCAT. So 37.5 grams of gold times the specific heat of gold. And my dog growled for the first time ever. That equals now the temperature of the gold is dropping from 83 to some other value, and then That equals the 100 grams for water, the 4.18, which is the specific heat of water. And then we're going, whatever that temperature is, minus 22, which is the original temperature. So this is going to be a higher temperature. You have to subtract 22 from it because that's your final temperature minus the 22 degrees that you started with. That's the change in the temperature. So from there we end up getting, let me get my calculator. So 37, whoa, not an error, we didn't even start. 37.5 times 0.129 is 4.8375. Now, I will distribute that to the x, but I also have to multiply that by 83. So that's 401.5, we'll call it, equals 418x minus 418 times 22 equals 9196. Alright, so from this point I'm going to add 9196 to both sides. And so that is plus 401.5 is 9597.5 minus 4.8375x equals 418x. So what do? I add 4.8375 to both sides. Oops. Yeah, x to both sides. So I end up getting now 9,597.5 equals, what is that, 422 point, we'll call it 8x. Divide by 422.8, divide by 422.8. Remember, x, which we are solving for, is the final temperature of this solution, because the temperature changed on one side from 83 down to whatever the value was, and here it went from whatever that temperature was, subtracting the 22 from it. Now, what is that final number? Divided by 422.8 gives us 22.7 approximately degrees Celsius. And that is A. That is not the change in temperature. That is the actual temperature as it stands once this problem is complete. All right, now this one, yes, there is a half-life formula, but I'm not going to hold you that or hold you responsible for that. There's a much easier way to do this. So 80% of the sample has to decay. 8.02 days. So I start my sample at day 0, I have 100%. At 8.02 days, I'm now down to 50% of what I had, and 50% is gone. I go 16.04 days, now I'm down to 25% is down, and 75% is gone. I go one more cycle, that takes us to 24.06 days. Now I'm down to 12.5% down, and I'm at 87.5% gone. So my half-life has to be somewhere in between 16.04 days and 24.06 days. And the only possible answer there is number 4, 19 days. There is a half-life formula. When you get to physics, that would be something to learn. You want to be a nuclear chemist? Absolutely something to learn. Do you need to memorize it in any other context? Not necessarily. Oxidation number. we had some rules about that. Now, can we see this on the screen? Yes, we can. Oxidation number. Except for peroxides, oxygen is always -2. Except for hydrides, hydrogen is always +1. So, this is not a hydride, this is not a peroxide. That has to be a -2. Each hydrogen here has to be a +1 if you remember your oxidation rules. Now this is something to remember for chemistry. This is extremely important. This is electrochemistry. If I have a -2 and have two +1s, what does that mean that my carbon has to be in order to keep this balanced? Well, the hydrogens and the oxygens are already balanced. So the oxidation number in this case for carbon is a 0 because there's no other possibility. When we don't have a peroxide and we don't have hydrides, that's what it has to be. Alright, moving over to the other side, and I have to do a little bit of lining up. We're back to intermolecular forces. A little bit further down. There we go. Something tiny bit cut off. Okay, this didn't line up right in my printer. I hope it did on the copies that I made for all of you. Anyway, compared to ionic compounds of similar molar mass, hydrocarbons typically have, now if you remember the hydrocarbons, hydrogen and carbon have very similar electronegativities, which means very little polarity. Ionic compounds are the opposite. Such a strong polarity, actually they're ions. They have, something has a plus charge, something has a minus charge. When you dissolve them in water, well then something like sodium and chloride, the oxygen part of water sticks to the sodiums, lets them dissolve. The hydrogen parts stick to the chloride, and everyone's happy. This, water doesn't know what to do with it. Water is a very polar molecule, doesn't know what to do with this. So, ionic compounds are going to be more soluble in water. Also, if they're not in water, this plus and this minus locks them into place. This, you only have dispersion forces holding them together, which is a much weaker force. So, when compared ionic compounds with similar molar mass, hydrogen compounds, hydrogens typically have, well, they don't typically have higher water solubility. They don't typically have higher melting points. So we're actually at neither 1 nor 2 in the case of that particular compound. Alright, now, next one. Alkanes, alkenes, alkynes. Alkanes are all single bonds, alkenes are double bonds, and alkynes are triple bonds. Generally, in most cases, the formula for an alkane is CnH2 plus N. 2N plus 2. I'm getting myself confused. 2N plus 2. That's exactly what we have here. That's an alkane. Alkanes have all single bonds. So, CnH2N plus 2. So this would be C is a 5. H2 would be 10 plus 2 is 12. That's a typical alkane. That's pentane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alright, so that's pentane. An alkene, which with a double bond, is usually CnH2n. This would probably be something with a double bond. So we'd have, and then a C, and then a C, and then C5. So C5, 1, 2, 3, 4, 5, H1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's also not going to have a triple bond. We see the same thing here. This is another alkene. The only possible alkyne would be the C6H10. Now if I have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is the answer Now, if you really remember your stuff, this would be called pentane, this would be called pentene, 1-pentene, if you really want to get technical, and this would be called hexane, hexane for the 6 carbons, and then ine with the triple bond. Alright, a student determined the density of a solid to be 2.90, 2.91, and 2.93. If the actual density of this solid is 2.70, how should the student's results be described? This is way back at the very beginning of the year. Let me slide it up a little bit. We talked about accuracy and precision. This is from the Chemistry Olympiad test, so it is obviously relevant and something that chemists who created this and chemistry teachers think you should know. I just want to make sure I can get everything onto the sheet. Okay, so all of these numbers are very close together. That's an indication of precision. But we compare it to an actual value, not very close. So this is definitely high precision and low accuracy, which your answer is B. A student is asked to measure 30 grams of methanol, but has only a graduated cylinder with which to measure it. A student is asked to measure 30 grams of methanol. We have the density, but has only a graduated cylinder with which to measure it. What volume of methanol should the student use to obtain the required 30 grams? Again, this is something just to remember from earlier on. Density equals mass over volume. So the density is 0.7914, and that equals 30 over V. Now, if you ask Dr. Carell, he would say that when you put, this is the good mark of an accelerated student, if they can handle a variable on the bottom, then they should continue with accelerated chemistry. I probably shouldn't have mentioned his name, and maybe I'll get in trouble for that. But that is what he says, and he'll stand by it, I'm sure. So anyway, my V's cancel out. I get 0.7914. V equals 30 divided by 0.7914 divided by 0.7914. The volume is going to be 37.96. So what volume of methanol should the student be used to obtain? Approximately 37.9. Actually a little bit over that number, which is interesting. But that's the closest answer. Which compound contains the highest percentage of nitrogen by mass? Now we're calculating molar masses primarily. If you just want to remember, I'm a little crooked. And I'm all the way. Let's move this up. There we go. Now, well, move it up a little bit more. Remember our empirical formulas from way back when. This is kind of the reverse of that. So in this particular case, I have 1 nitrogen, 3 hydrogens, and an oxygen. So that is, 14 plus 16. That is 30. 33 grams per mole, and then 14 grams of that is from nitrogen. So the percent would be the percent of my the amount of my nitrogen, the grams of my nitrogen divided by the total times 100. It'd be 42% nitrogen. Second one, I have 1 nitrogen, 2 nitrogens, 28. I also have 2 oxygens, 32. 28 plus 32 is 60. And then I have 4 oxygens, so that's 4 hydrogens. That's a total of 4, so that's a whole 64. 28 divided by 64. The amount of nitrogen divided by the total times 100, that gives me 43.75. In the next one I have 28 plus 48, because it's 2 times 14 plus 3 times 16, so 28 plus 48 is 76, and then 28 divided by 76 is 36.8%. The final one is 2 nitrogens, a carbon, 2 oxygens. I can already tell that my level of nitrogen there is going to be lower, but just to humor myself, 28 plus 4 is 32. 32 plus 4 is 34. 34 plus 12 is 46. 46 plus 32, I can do it in my head, but I'll do 78. And then I have 2 nitrogen, so that is 28 divided by 78, which is 35.8 also. So my highest percentage would be for for letter B. Alright, last one. What is the density of ammonia gas at 2 atmospheres of pressure and a temperature of 25 degrees Celsius? That looks like quite a challenge. If I could figure out how many moles... Alright, sorry, I just lost another piece of lead from my pencil, but I have 2 atmospheres. I can use the ideal gas law to solve this. Now, this will make up for the problem that I repeated on the ideal gas law. I'm sorry, on the gas law quiz. This will make up for it, because this is another ideal gas law problem. Probably the one I should have put with the duplicate on the practice test, but we'll make up for it right now. So what is the density of ammonia gas at 2 atmospheres of pressure, temperature of 25 degrees Celsius? Well, the 25 degrees Celsius needs to be turned into Kelvin. Atmospheres will have to be turned into kilopascals if I'm going to use my R value of 8.31. So I need, there's another, come on. All right, there's another piece gone. So I need to do P, which is 2.00 times 101.3 over kPa over 1 atmosphere. I should write my units. Come on. Just so we're not confusing ourselves, it's 2.00 atm times, okay. So this ends up being 202.6 kilopascals because my units canceled out. Alright, so now I have 202.6. What do I do for volume? Well, I'm going to find my density in grams per liter. So why don't I just use 1 liter? Am I allowed to do that? Absolutely. It doesn't tell me a volume. I can assign any volume. It just so happens my density is going to have to be grams per liter. So if I find moles per liter, and I take those moles and I turn them into grams, well then I'm in great shape. So I don't know N. R is 8.31 because I converted my kilopascals to, I converted my atmospheres to kilopascals, and then my temperature is 298. 298 Kelvin. All right. Maybe from now on we're going to use pens. All right. So 8.31 times 298 equals, so divide this side by 2476.38. I divide the other side by the same number, 2476.38. Okay, so 202.6 times 1 divided by 2476.38 equals, N equals 0.0818 moles of ammonia. That's how many moles of ammonia I have in 1 liter at 2 atmospheres and 25 degrees Celsius. So now all I need to do is multiply that by the gram molar mass of ammonia, and ammonia is NH3, which means 14 plus 3 is 17 grams over 1 mole. So I enter that into my calculator and I end up getting 1.39 grams per liter. With that, we have completed both sides of the sheet. For concepts to remember, we've done some review for our final, and we are done. I will hope to post the entire packet on gas laws sometime soon as well.